So we've come to an important impasse in the video. We've done a fabulous introduction, we've done a very specific aim, and we've defined the variables that we're using so far. Quick recap on the variables. S is the number of symbols per card. So here, 1, 2, 3, 4, 5, 6, 7, 8. S is 8. We have N sub S is the minimum number of cards we need to make a deck. And we had CIS, which denotes which number card you are in the deck of S symbols. So for example, this one could be the first card in a symbol of 8, so it would be C18. Just to recap you on those symbols if you're joining us a little bit late in the series. Now we're going to start digging into the mathematics. So we're going to start by looking at the first card in our deck. Now remember, our deck, we've replaced symbols with numbers to make the math easier, and instead of starting with 8, which is going to produce some really big numbers, we're going to start with just 3 symbols per card. Not 3 symbols in total, 3 symbols per card. The first question asks us, okay, what is the sample space of all of the possible distinct pairs on the first card if I have 3 symbols? So to discuss this, we're looking now only at one specific card. You see, I've left one card here. And what a distinct pair would be, for example, Death Eater and the Thunderbolt symbol. Or it could be Lucius Malfoy and a spider. Or it could be a magic key and the Slytherin symbols. So we're focusing in on one card and we're seeing how many distinct pairs our card would have. Well, if I look at my card here with 1, 2, 3 on it, I can have the following combinations. I can have 1 with 2. I can draw it out for you here. 1, 2, 3. 1 with 2, or I can have 1 with 3. I could also now have, I can't do 2, 1 because that's the same pair as 1, 2. The order is not important, but I could have 2, 3. So how many combinations of 2 symbols could be made from the symbols on the 1, 2, 3 card? Okay, that would be, there were 3 pairs here. And we've defined that as NC13, the number of distinct pairs on the first card with 3 symbols. We need to explain why the pair 1, 3 cannot appear together on another card. It can only appear on the first card. And the reason for this is each pair of cards can match once and only once. So, for example, if I had a second card here, okay, it could have a number 1 on, and that could be the match, for example, here. But then it could not also have number 3 on it, right? Because if it had the number 3 on it, it wouldn't be matching once, it would be matching twice. So the pair 1, 3 can only be found on the first card in our deck. We can have a 1 somewhere else on a different card, we can have a 3, but 1 and 3 together can only appear on that first card. Okay? Now it says, why are the set of sample spaces of combinations of cards for each of the I cards with S equals 3 mutually exclusive? Okay? And that's because what we just talked about, that for each pair, if it appears on one card, that same pair cannot be on another card. Otherwise, those 2 cards would match in not 1, but 2 places. So, in this last part, we're asked to write an expression for the number of distinct pairs for each card in the union between 2 different cards. Okay, so for example, imagine you had 2 different cards here, and you're looking at how many pairs in total between the 2 cards can we have? Well, in our case, for our deck of cards that have 3 symbols per card, you would have 3 pairs for the first card and 3 for the second card. And as we've discussed here in C and D, they would have no common pairs, which means here the number of pairs in total between the first and second card would just be 6, or 3 add 3. okay? So in this case, if I compare the number of pairs in the first card with any other card in the deck, I can just add them together. And you would have to subtract 0. This comes back to the identity you guys may have seen before, which is n of A union B is equal to n of A plus n of B minus the intersection of A and B. That's the first section done, where we talked about the distinct pairs for a single card, and then we're going to be moving on to some more interesting maths in the next part of the series.